Okay, so the second video for our week 4 remote learning lesson is we are going to talk about the different ways you can evaluate limits, specifically algebraically. So far we've talked about the numerical approach, so that's creating a table and seeing what y value it gets really, really close to. The graphical approach, right, just graphing it and then looking at the graph. And then remember going from both sides, so left and right hand side. So then this, right hand side. And so this video focuses on the algebraic approach. So how we do this. So before we get into talking about how to do it algebraically, I know you're asking yourself, why can we say this? The limit does not exist, right? Hopefully when you heard limits, that's the first thing you thought of was Miss Lindsay Lohan and Mean Girls. And I like to pretend I am Tina Fey of my life, so there you go. Just teaching you how to do this. So there are different ways that we can determine when the limit does not exist. So if we look at the specific value, which is what we talked about, or I kind of hinted at in the last video, is if you look here. So what is the limit as you approach 0 from the right? So as I'm going from the right, the limit is 1. But yet as I'm going from the left, the limit is -1. Therefore, if I am going in both directions and they do not approach the same value, then this is where the limit does not exist, okay? So does not exist for 0. Right? If I said the limit, so when I write it like this, the limit as x approaches 0 from the right of f of x, it equals 1. And the limit as x approaches 0 from the left, f of x, it equals -1. That's okay. But if I am trying to, if you see it up here, say the limit as x approaches 0, so meaning just overall, then this is where you say it does not exist. And I would prefer, if you would use this DNE abbreviation, one, it just makes your life easier, and all caps is how we write it, does not exist. Okay, so that is when the limit does not exist. If we can see on the graph, it approaches 2 different values, then the limit does not exist. Another time it does not exist is when it's unbound behavior, meaning as we look here, as x is approaching infinity, well, if you look at infinity, it is going to -infinity or infinity, so that doesn't work. And then if you look here, as x approaches 0, it does not reach a spot, right? It just keeps going and going and going. So therefore, it does not exist. And then the other time is if it's this oscillating behavior, where if it flips from 1 to -1, 1 to -1, it just means it will never, never, never stop. So then it doesn't work. So again, the 3 key things of when a limit fails to exist is the f of x approaches a different number from the right side of c. Then remember, this is that designated, I hope I spell correctly, designated x value. Okay, so that if it doesn't have the same left and right hand behavior, then it doesn't work. Or if it is without bound, meaning it goes on forever, it's infinite, like that last example was 0, then it doesn't work. Or if it oscillates between 2 fixed values as x approaches c, then it does not work either. Okay, this is the one you're going to see most often, is that it approaches a different number from each side. So if a limit exists, so the limit of a function as x approaches c is the function value at x equals c, f of c, if it exists. Meaning, right, like if we think of the limit as x approaches 1, and let's say our function is 2x minus 3. Well, what is that function? That's a linear function. You know there's not going to be any weird holes or anything. That means I can do f of c, right? If we have f of x and we have our function is 2x minus 3, f of c means everywhere we see an x, we replace it with whatever the c value is, right? The designated x value. So 2 times 1 minus 3, so it is 2 minus 3, so -1. So that is the limit. If it does not exist, then it might be, so meaning if f of c does not exist, meaning it's like there's a hole on the graph where we get something weird like 0 over 0, then you see what value would fill that hole. And if you can't fill that hole, what makes it continuous? So if I come back to here, right? If we looked at the limit, 1, 2, 3, at the limit as x approach 3, technically f of 3 doesn't happen, right? Does not exist, right? Because there's this hole right here. But since the value of 1 fills that hole, that is why the limit is 1, okay? That is what it means. The only time limits don't exist, well, not only time, but the main time limits don't exist is when they have two different values, okay? That is what that meant when this part. What if you can't fill the hole to make it continuous, okay? Then we have these techniques in order to find it. So let's say I plug in 1 here, okay? So before I talk about how we would evaluate, let's see if I plug in 1. Well, 1 minus 1, and then I'm going to plug in 1 cubed minus 1 squared plus 1 minus 1. Whoops. Well, if we look at this, 1 minus 1 is 0. Then 1 cubed is 1, minus 1 is 0, and then 1 minus 1 is 0. So I get 0 over 0, right? That's something that doesn't exist. So if I plug 1 into this function, it does not work. Or if you notice, it says factoring / dividing out. So if you can factor, if you can do all of the algebra we have reviewed, right? Factoring, rationalizing the denominator, multiplying by conjugates. This is why we've been reviewing all that stuff, or why we spent time reviewing that this school year, is so you are able to find limits and use these skills in calculus. So if I look at this one here, we can factor by grouping, right? So our numerator is already factored out. So what's the GCF here? So I'm going to write this work down here. And then my other group is x minus 1. Well, the GCF of those two is x, so I'm left with x, or actually it's x squared. My bad. So then I'm left with x minus 1, and here the GCF is only a positive 1, so it's x minus 1. So we have x minus 1 is one of my factors, and x squared plus 1 is one of my factors. Well, if you notice that, these two now cancel out. And remember, the only time we can cancel this stuff out is if they're multiplying here, right? Because that's its own parentheses. So now I have 1 over x squared plus 1. Well, what happens now if I plug 1 into this function? So we now have the limit as x approaches 1 of that. So then now I'm going to do 1 over 1 squared plus 1, which is 1 over 1 plus 1. So it equals 1/2. That is the limit. Okay, so since we were able to cancel that out, we now found the value that would fill that hole and would make it happen. Okay, so another factoring one. Okay, this is just good to review our factoring rules. Again, if I plugged in 5, 5 minus 5, 5 squared minus 25, 5 minus 5 is 0, 25 minus 25, okay, I get 0 over 0 again. That's not okay. So technically the function doesn't exist at 5, but I notice here it's a difference of squares. So remember, you just take what's the square root of x squared, x and x, what's the square root of 25, 5 and 5, and since it's a difference, one's plus, one's minus, x minus 5 is in both of those. So I now have 1 over x plus 5. We're going to plug 5 in. 5 plus 5. So I get 1/10 is the limit. Okay? So that's factoring, and you're going to see a lot of that. So another example where you might see difference of squares. What if I had x to the 4th minus 16? Well, if you notice here, technically this is the difference of squares, right? Because 16 is a perfect square. But also x to the 4th, because I get x squared. And then I get plus 4 minus 4. Oh, look. Now, okay, we can't do anything with this one, but there's another difference of squares, where this becomes x plus 2 times x minus 2. That's what this factors down to. So just keep in mind that you might see some factoring hint. You're going to see some factoring like this, where you might have to do a difference of squares and then another difference of squares. Okay, so just remembering those factoring rules. I know we haven't done that in a little bit. We kind of did with some trig. So just make sure that you're going back and looking at those factoring rules. All right. So rationalizing, multiplying by the conjugate. Again, if I plug this in, well, we already have 0 in the denominator, so we know it's not going to work, okay? So how we do that, remember the conjugate it stays the same. So when you multiply the conjugate is usually when you have some square roots involved, okay? So if you see some square roots, that means you're going to multiply by this conjugate. And remember, it's opposite. So it's x plus 1. That stays the same, but this now becomes plus 1. And then whatever you do to the bottom, you do to the top. So if I do the square root of x plus 1 times this, well, remember when you multiply by itself, right? A radical by itself, it just becomes x plus 1. And then this is plus the square root of x plus 1. Then now we do negative square root of x plus 1, negative 1. These two cancel out, so we have x plus 1 minus 1. Those cancel out, so we're left with x in the numerator. And then I'm going to just leave the denominator, as x times the square root of x plus 1 plus 1. And why I do that now, these x's cancel out. So I'm left with 1 over the square root of x plus 1 plus 1. Now let's substitute what happens when we put 0 in. So then that becomes 1 over the square root of 1 plus 1, which is, whoops, I keep thinking ahead in my head because that's 1. So it just is 1/2. All right. So let's do another rationalizing multiplying by the conjugate. So square, again, we have 0 on the bottom, so that's not okay. So 7 minus x plus the square root of 7 all over this times itself. So square root of 7 minus x minus the square root of 7 times the square root of 7 minus x plus the square root of 7. So this times this is itself. So 7 minus x. This times this is that plus square root 7 minus x times square root 7. Then this becomes minus square root 7 minus x times square root 7. And then this times this is negative 7. All right? These two cancel out. So we have 7 minus x minus 7. These two cancel out. So I'm left with negative x. So I have negative x over x times that jargon. The x's cancel out, so I now have negative 1 over this. So then we're going to plug in 0. So we have 7 minus 0 plus square root 7. So I now have negative 1 over the square root of 7 plus the square root of 7. And then now I have negative 1 over 2 square root 7. I'm okay if you leave it like this. You don't have to worry about rationalizing here, okay? All right, so then there's that one. So, like we talked about earlier, one-sided limits. So just a refresher, when it's a little negative sign, that means left-hand side. And then if it's this little plus sign, it means right-hand side. So, one-sided limits here. So if you look at this, the absolute value of 2x over x, as I approach 0 from the left, I get close to negative 2. But as I approach 0 from the right, I get to 2. So the limit as x approaches 0 of this, well, what happens again if there are two different ones? It does not exist. Okay, and you would just write that, does not exist. All right, so my last example for you here is, this is going to lead into what we do next week. So a limit from calculus. So for the function f of x equals x squared minus 2, and then we're going to find the limit of f of 3 plus h minus f of 3 over h. So I got to find each one of these first before we plug it in. So remember function notation. If it's 3 plus h, that goes into this spot here. So f of 3 plus h is going to be 3 plus h squared minus 1. Well, 3 plus h squared is 9 plus 6h plus h squared minus 1. And how I know, remember that, I don't know if you guys notice the trick really quick when you do this, right? 3 plus h times 3 plus h. When you do this, it's always, if this is a plus b, it's always a squared. Well, what's a squared? 3 times 3, 9, plus 2ab, because we're doing 3 times h 2 times. Well, 3 times h is 3h, so 2 of those is 6h, and then you do b squared. So that's how I get h squared really quick. Okay, anyway, then we combine these two. So now, and I'm going to just rewrite it in standard form, h squared plus 6h minus, or plus 8. So that's this first part. So the limit as x approaches 0, we have h squared plus 6h plus 8. So then now we're going to do minus f3. So f of 3. We're going to do 3 squared minus 1. 9 minus 1 is 8. So minus 8 all over h. Okay? So if you notice here, these cancel out. I'm going to go back to the blue. So the limit of, and it shouldn't be x minus 0, it's h minus 0. That was a typo on my part. H minus 0. We're now left with h squared plus 6h over h. If you notice here, some of you know to cancel stuff out here. Why we can cancel out. Is there a GCF of those two? Yes, the GCF is h. So now we're left with, in our numerator, h times h plus 6 over h. So we can cancel out those h's. That's why I know I can cancel those out, not because of this addition sign here, and they both have h's, but because the GCFs, I can return it into multiplication so it cancels out. So we're now finding the limit as h approaches 0 of h plus 6. Well, that's 0 plus 6, so the limit is 6. All right, so you have a couple of limit assignments to do this week. 2 are on Schoology. 1 is in your textbook. So please, please, please make sure that you guys reach out if you have any questions and attend the office hours, because this is some new stuff. So it might be a little bit weird to do. All right.